Hello mathematicians. Today we see one nice problem asked regarding diagonalizable matrices. So in the last 5-6 videos we are seeing many problems on diagonalizable matrices. Okay, so I'll explain the question. So this is asked in June 2013. It is a part C problem, and A is a complex 3 by 3 matrix. Okay, satisfying A cube equal to minus I. Which of the following statements are correct? Okay, maybe options I will just zoom and I'll show you. So if a matrix satisfies A cube equal to minus I, then the options are A has three distinct eigenvalues, A is diagonalizable over C, A is triangularizable over C. This may be something new for many people, but it is a very simple concept. Then A is non-singular, base or determinant of A is not equal to 0. Okay. Now let's do one option after the another. So first they are saying that if A is any matrix satisfying A cube equal to minus I, then A has three distinct eigenvalues. Okay, so whenever you see some problem in which they are saying A satisfies some property and they are asking some question, always first find some simple matrix satisfying this condition. That is our first step. Okay, then using that option we try to eliminate as many options as possible. Okay, now one simple example of a matrix satisfying A cube equal to minus I is A equal to minus I itself. You take A equal to minus I, then A square will be I, then A cube will be minus I again. So if you take A equal to minus I, its eigenvalues will be minus 1, minus 1, minus 1. Okay, so clearly this doesn't have distinct eigenvalues. Therefore, we can conclude that first option is wrong. Okay. Okay, so let's move on to the remaining options. Next we will show that A is diagonalizable over C. Okay, uh, so again solving one problem should not be about solving that problem. Using that problem, you should be able to solve many such similar problems. Okay, so now I'm going to tell the proof of the fact that if a matrix satisfying this condition, then that matrix is diagonalizable over C. But from that proof, we can we can observe that uh, A be a complex matrix of any order. Here they are given this is 3 and this is 3, both are same number. But in general, you take any k by k matrix. Okay, and assume that it satisfies a power n equal to minus I or a power n equal to plus I. Anything doesn't matter, minus I or plus I. Note that I am taking k by k matrix, but I am taking a power n equal to. So this k and n need not be same. Okay, so our what we going to really prove is any complex k by k matrix satisfying a power n equal to I or a power n equal to minus I, that is always diagonalizable over C. So the same problem, if tomorrow it's asked for 7 by 7 matrix satisfying a power 100 equal to I, still we know the answer, that matrix is going to be diagonalizable. Okay, let's see why is it so. So it is given that A belongs to M3 of C, and so it is M3 of C means 3 by 3 complex matrices, and A cube equal to minus I. What does it mean? It means that A satisfies the polynomial x cube plus 1 equal to 0. Okay, now it is you can clearly see that minus 1 is a root of this polynomial. Therefore, x cube plus 1 equal to x plus 1 times x square minus x plus 1. So yeah, you can easily find this degree 2 polynomial. Now we calculate the discriminant of this polynomial. Okay, so discriminant of this polynomial p square minus 4ac will be minus 3. Therefore, we get x is we get that this polynomial has distinct roots. Okay, because discriminant is less than 0 means this polynomial has two distinct complex roots. But this is a real polynomial. For real polynomial, complex roots occurs in pairs. Therefore, the zeros of this root are alpha and alpha bar, and alpha is a complex number, non-real complex number. Okay, it cannot be real number. If alpha is real number, then we get alpha equal to alpha bar. we will get these two roots will be real. But since the discriminant is strictly less than 0, these two number alpha cannot be real, and alpha bar are non-real complex number or purely complex number, let's say. Therefore, what are the roots of this polynomial x cube plus 1? First root is minus 1. Second root is alpha, which is a complex number. Third root is alpha bar. Okay. Therefore, this polynomial has distinct roots. Okay. So that is the first observation. Once you saw a polynomial as distinct roots, then regarding the diagonalizability, we are in a very safe zone. Okay. Now it is given that a cube equal to minus I. That means that a satisfies this polynomial. And what we know from our uh, what we know regarding minimal polynomial divides all the polynomials satisfied by a. Therefore minimal polynomial should divide x cube plus 1. Okay, so I shall denote the uh, okay, so x cube plus 1 is a polynomial satisfied by a. Therefore minimal polynomial, what is the notation for minimal polynomial? Ma of x. Okay, so the minimal polynomial divides x cube plus 1. Okay, since minimal polynomial divides all the polynomials satisfied by a. Okay, now if a polynomial p of x divides q of x, then every root of the roots of p of x is a subset of roots of q of x. Okay, set of roots of p of x should be contained in set of roots of q of x. Why is it so? Because since p of x divides q of x, you can write q of x equal to p of x times some r of x. So whenever this p of x is 0, then q of x also has to be 0. Okay, therefore we conclude that the roots of p of x is contained in roots of q of x. Therefore now minimal polynomial of a divides x cube plus 1. Okay, therefore roots of this polynomial is subset of roots of this polynomial, but this polynomial has distinct roots. We just saw that roots of this polynomial is minus 1, alpha and alpha bar. Therefore minimal polynomial of a also has to have distinct roots. Okay, therefore, the minimal polynomial of max of a is also has distinct roots. Okay, what is the meaning of it has distinct roots? It means that ma of x splits into distinct linear factors over c. Okay, um, for example, if lambda 1, lambda 2, lambda 3 are the distinct roots of minimal polynomial, then what is minimal polynomial? Then minimal polynomial is x minus lambda 1 and x minus lambda 2 into x minus lambda 3. Okay, since lambda 1 and lambda 2, lambda 3 are distinct, we see that this polynomial is product of distinct linear factors. Or we can say that this polynomial is splits into linear factors. Okay, therefore, if since the minimal polynomial has distinct roots, minimal polynomial splits into distinct linear factors over C. So x cube plus 1 has distinct roots in C. Therefore, minimal polynomial also has distinct roots in C. So that means that minimal polynomial splits into distinct linear factors over C. Okay, if minimal polynomial splits into distinct linear factors, that means that A is diagonalizable over C. Okay, okay, so we have concluded that A is diagonalizable over C. Okay, now we go through our proof. So next option is A is triangularizable over C. Fourth option is A is non-singular. Now if you see, it is given that a cube equal to minus I. So you can apply determinant on both sides. We get determinant of a cube equal to determinant of minus I, that is minus 1. Okay, but determinant of a cube is equal to determinant of a whole cube. Okay, determinant of a power k equal to determinant of a whole power k. Okay, so we get determinant of a whole power cube equal to minus 1. That means that determinant of a is not equal to 0. Okay, if determinant of a is 0, then its whole cube cannot be minus 1. Okay, so we get a is non-singular. That is true for sure. So what remains to do is the triangularizable. So let me phrase the definition of triangularizable matrices. Before going to triangularizable, we just saw that this polynomial x cube plus 1 has a distinct roots. Therefore, if a matrix satisfies this polynomial, then its minimal polynomial should divide this polynomial. Since this polynomial has distinct roots, minimal polynomial will have distinct roots in C. Therefore, that matrix will be diagonalizable over C. Correct. Now, the same idea can be used for for a more general case. So, let me first explain that. Okay. Uh, okay. So, consider the polynomial f of x equal to x power n plus 1 and g of x equal to x power n minus 1. Two polynomials we are considering. Then what is f prime of x and g prime of x? We get f prime of x and g prime of x equal to n times x into n minus 1. Now, what are the roots of this polynomial? 0 is the only root of this polynomial. All the roots of f prime of x and g prime of x are equal to 0. Okay, but 0 is not a root of f of x and g of x, correct? 0 is not a root of this polynomial. So that means that f of x and f prime of x has no common roots. Similarly, g of x and g prime of x, g of x and g prime of x has no common roots. Okay, that means that f of x and g of x has no repeated roots. Okay, why? Because if alpha is a repeated, if alpha appear as a root of f of x at least two times, okay, then alpha will be root of f prime of x also. Okay, so if alpha is a repeated root of f of x, then alpha will be root of f prime of x also. Why is it so? Suppose a is a root of f of x at least two times. Okay, why at least two? Because for g of x also a can be appear as a root. Then what is f prime of x? F prime of x equal to, you can use the product rule. You get 2 times x minus a times g of x plus x minus a whole square g prime of x. Okay, now you can take out this x minus a common. You get so x minus a times some polynomial. Therefore, x minus a is also a factor of f prime of x. Okay, so if therefore we conclude that if a is a repeated root of f of x, repeated root means appears at least twice, then that a has to be a root of f prime of x. Okay, that is our result. So now in our example, so we have concluded in our example uh, f of x and f of x and f prime of x has no common roots. Therefore, all the roots of f of x are distinct. Similarly, g of x and g prime of x has no common roots. Therefore, all the roots of g of x are distinct. Okay. Therefore, suppose a matrix, if it satisfies this polynomial or this polynomial, then its minimal polynomial should satisfy this polynomial or this polynomial respectively. Okay, so for example, let's deal with this polynomial. So minimal polynomial should divide this polynomial, but this polynomial has repeated roots, I mean sorry, distinct roots. Therefore minimal polynomial also has to have distinct roots. If minimal polynomial distinct roots means that it splits into linear factors, therefore the matrix will be diagonalizable over C, because the roots of this polynomial is uh, C, will be in C whenever n greater than or equal to 3. When n equal to 2, this polynomial has real roots, but even this polynomial for n equal to 2 also it will have complex root only. Okay. Okay, it will have some real root, it will have some complex roots, it will have some real roots, some complex roots. Okay. Okay, so in general, unless n so if n is greater than or equal to 2, this will have complex roots always. If n is greater than or equal to 3, this will have complex root always. Okay, that is our conclusion. um, Therefore any matrix satisfying this polynomial or this polynomial has to be diagonalizable over C, and the matrix order is irrelevant. Whatever matrix order, 100 by 100, 1000 by 1000, if it is satisfy some x power 5 plus 1, then that matrix has to be diagonalizable over C. Okay, that is our conclusion. I hope you understand the more general result regarding matrices satisfying this condition. That is one thing. Now we'll talk about triangularizability. I will say what is mean to triangularizable. If you know the definition of diagonalizable matrices, then the definition of triangularizable matrices is similar. A matrix M is said to be triangularizable over a field F. That is what important. Always we have to say triangularizable over what field. Okay. So triangularizable over a field F if there exists an invertible matrix P with entries from the field F such that PA P inverse equal to T, where T is an upper or lower triangular matrix. Okay, so we know, you guys know what is a upper triangular or lower triangular matrix. So usually like 1, 2, 3, 0, 2, 3, 0, 0, 3. This is an example of upper triangular matrix. So similarly, you can define lower triangular matrix. So if there is an invertible matrix P such that PA P inverse is either lower triangular or upper triangular. I mean, if you can bring it to lower triangular, you can bring it upper triangular also. So it doesn't matter. So if you get a diagonal matrix, we say diagonalizable. If you get a triangular matrix, we say it is triangularizable. That is the difference. So we have seen many results for diagonalize a matrix. Here we have a necessary and sufficient condition for triangularize a matrix. Okay, if a matrix has all the eigenvalues in a field F, then A is triangularizable over a field F. Okay, so this is also a necessary and sufficient condition. You can think of it as a if and only if. Okay, A is triangularizable over F, then it has all the eigenvalues in the field F also. So the proof of this result again can be seen in the linear algebra of Rydberg and the linear algebra Hoffman and Kunze. Okay. So in particular, if F is algebraically closed, then every matrix is triangularizable over F. Why? If it is an algebraically closed field, means every polynomial over F will have roots in the field F itself. Okay. So if you consider a matrix over a field F, which is algebraically closed, then the characteristic polynomial of the matrix will be a polynomial with coefficients from F. And since F is algebraic closed, its eigenvalues will be in F. Okay. Once the eigenvalues are in F, it is triangularizable. Therefore, if F is algebraically closed, then every matrix in F means matrix with entries from F is triangularizable over F. Okay. Okay. Good. So now C is algebraically closed. Okay, since C, every polynomial over C has a root in C, at least one root. Actually, all the n roots will be in C. Therefore, we conclude that A is triangularizable over C. Okay, okay, guys. I hope you understand the problem clearly. If you have some doubts, please let me know. I will meet you guys with some different problem. Thank you, guys.